Hi everyone, welcome to Negrom seminar. Today our speaker is Samuele Rubino from University of Sevilla, and he will talk about reduced order modeling for Navier-Stokes time splitting methods with open boundary conditions. The floor is yours, Samuele. Thank you so much.
Okay, thank you too. Hi everyone, and thank you first all the organizer for inviting me to give a talk in this NAG-ROMS seminar series. So my intention here is to present a recent work we have done in collaboration with Professor Mehdi Azayes from University of Bordeaux, Professor Tomás Chacón from University of Seville, and Carlos Núñez, which is our PhD student, both from University of Seville and also the enterprise virtual mechanics SL, since he is doing an industrial PhD. And we want to talk about a reduced order modeling we have applied to a particular case of Navier-Stokes time splitting method, where we consider open boundary condition. So here, what I will introduce during the talk in the first part will be the full order model in the framework of finite element we are going to use, and then the corresponding reduced order model we have tried to get from it. So here you see, okay. So here you see basically the outline of the talk. So first of all, I will introduce a fully discrete time split scheme by considering open boundary conditions. So the focus will be on the time discretization, where we are going to use a non-standard pressure correction scheme in order to improve basically the pressure boundary condition in a non-standard way. So this is basically a method that has been previously introduced by the group of Professor Mehdi Azayes at University of Bordeaux in the framework of finite volume methods. So here the intention is to extend it to finite element method, and then to get the advantage of it in order to get also a reduced order model from it. So in the second part of the talk, I will describe in detail the fully discrete reduced order model applied to the phone, which basically is based on an hybrid strategy, let's say, which is both data-driven and based also on Galerkin projection. So it is basically based on the POD-ROM methodology, but we will use on one side the POD-Galerkin intrusive strategy basically in order to reduce some step of the time splitting algorithm related to the predicted velocity and so on, and then a radial basis function technique in order to compute basically the pressure boundary condition and related equations. So in this case, actually, we do not use any supermiser strategy technique. Neither stabilization term are needed for the algorithm that we are going to implement. And finally, we applied it in order to see the performance of this method. We applied it to the numerical simulation of a 2D and steady flow past the circular obstacle at laminar regime. So here we will see how we can get good results with this strategy, both for quantity of interest such as drag coefficient or lift coefficient around the obstacle, but also we are able to compute, let's say, the whole field, for instance, of velocity and pressure, which is of particular interest. We have, for instance, in application where we have for instance, the airflow around wind turbines and so on. And we will see how we get a really good computational efficient algorithm by doing both time splitting at the full order model. So in order to compute all the snapshots required in the offline phase. And also we will exploit basically then the computational efficiency in the with the reduced order model. So here is the contents of the talk, and we start actually by giving a brief description of the Navier-Stokes equation model problem we are going to consider. So let's consider omega as our bounded domain in dimension 2 or 3, with gamma, which is Lipschitz boundary, and actually we are going to split it into two parts, a part in which we are imposing, let's say, inlet boundary condition, or where we are considering basically the wall of the domain, which is gamma D, where we actually impose Dirichlet condition, and the other part, which is gamma N, which is the one where we consider the open boundary condition. So in one, you can see the incompressible Navier-Stokes with this mixed boundary condition, where as usual, U is the velocity field, P the pressure, nu the kinematic viscosity, and F the forcing term. So, and for simplicity, actually, here we are considering just homogeneous boundary, Dirichlet boundary condition on gamma D, but actually it can be easily extended to the non-homogeneous case by a proper lifting technique. So first of all, we are going to give the variational form of the continuous problem. So by x, we are denoting the velocity space, which is actually h1 space with zero boundary, Dirichlet boundary condition gamma D, and by L2 the pressure space. So here is the variational formulation of the problem we consider, where with parentheses we are going to denote the standard L2 inner product, and with this symbol we are considering the duality pairing between the velocity space and its dual. So once we have it, we pass to treat the fully discrete full order model, as I said, by focusing in particular on the time discretization. And thus, here comes the idea to consider a non-standard pressure correction schema for open boundary condition in order to get basically more precise results with respect to standard approach for the pressure boundary condition in case of open boundary, and also a better convergence order of the method if we compare it, for instance, to standard splitting schemas such as Chorin-Teman and so on. So yeah, basically in this part I will explain in detail how we treat this pressure boundary condition, and then we will get the fully discrete full order model by considering it in a finite element framework. So in order to start, we just consider the semi-discrete in time version of the continuous problem, and this is done for simplicity in order to highlight just the pressure boundary condition that we are going to use, and then we will pass to the fully discrete version of the algorithm. So in order to describe it, we are going to use a semi-implicit Euler scheme. So once we have it initialize the velocity condition, here is the description of the iteration in time once we have considered a discretization of the time interval and so on. And so this is basically the monolithic version of the problem in which we couple both velocity and pressure. And now we are going to split this unknown. So in order to do it, we are going to consider a pressure correction scheme. So first of all, we are going to compute a predicted velocity that I call U tilde by basically a convection diffusion problem. So in step one, we can see the prediction diffusion problem for U tilde, which is actually the predicted velocity that respect the homogeneous Dirichlet boundary condition gamma d, but for which we do not require that it is divergence zero. And from once we have computed this U tilde by using a previous pressure, then in step two we are able to compute at the same time the corrected velocity and the difference and the pressure difference. So in step two, we are actually considering a pressure continuity correction problem in which we have that now the corrected velocity as divergence zero, but on gamma d satisfy just that the un plus 1 dot n is equal to zero. And finally, we can also recover the pressure by the last simple formula. So here we omit for the moment what are the let's say the right boundary condition we have to impose on gamma n, because in standard, as usual, what people in general do is to impose directly that phi n plus 1 is equal to say 0. That means that basically Pn plus 1 is equal to Pn, and if we go on with this strategy, we have that Pn plus 1 actually is equal to the initialization of the pressure. But as we know, this in the majority of cases, this can cause some numerical issues on the open boundary. And so in this case, we have decided to go with an alternative strategy, and then I will focus on it. In any case, before to pass to the detailed description of the pressure boundary condition gamma n, so just to say that step two can be seen actually as by its primal formulation, so as a Poisson problem by just applying divergence to step two. And so we actually get a Poisson problem for the pressure difference with this condition on gamma d, and with the condition that I will go to describe on gamma n. And finally, we can update both pressure and velocity as we see in 7 and 8. So as I said now, the strategy to compute to complete or to close this algorithm for problem 6 is to define correctly the boundary condition on gamma n. And for it, we have used the idea coming from this paper by Mehdi Asayas and co-worker, published on JCP in 2011, where they treat in a finite volume framework the improvement on open and traction boundary condition for Navier-Stokes time splitting methods, and have also done a thorough, let's say, numerical investigation, both for academic tests, so seeing really the convergence order of the method, and also apply to more complex tests such as the flow around the cylinder that we will see in this case. And so to exactly define the boundary condition for the pressure difference in step 2, I will describe it for a simplified domain. So let's consider a channel in 2D and just put gamma n as the right boundary of amplitude 2L. So the definition of the right boundary condition for pressure difference start by taking the first component of the first equation here of 5 and derive it on x1 direction. And then if we project the open boundary condition of that we impose both for u and u tilde on x1 direction, we easily get equation 10 and 11. And finally, combining these last 3 equations, we obtain actually the pressure boundary condition that we are going to impose on gamma n. So this is not the final version we are going to implement, because we can get an easier version to implement, which comes from subtracting this equation in the first equation of 6 that you see here. And thus we do it in order to have a boundary condition on gamma n, which is actually an ordinary differential equation that is just in which we have a derivation just on vertical direction. And so actually the pressure boundary condition that we are going to impose on gamma n is a non-homogeneous Dirichlet condition for the pressure difference that comes from imposing that the pressure difference is equal to the solution of the 1D problem that we see here on gamma n. So once we solve this 1D problem on gamma n, we get the solution phi hat, and this is the one that we impose as boundary condition for the pressure difference on the outflow boundary for the pressure difference. So this basically closed the problem, and now we are just going to give a finite element space approximation of this technique. So basically we consider internal approximation of the continuous space for all the unknown fields, which are the velocity, the prediction velocity, the pressure difference, and the pressure difference boundary space. And once we have the corresponding finite element approximation, so we have for step 1 this prediction diffusion finite element approximation, then we pass, once we know the predicted velocity, before to pass to the step 2 of the computation of the pressure difference, we have, as we have seen before, we need to solve first the pressure difference boundary finite element approximation, okay, which is given here in 16, and then we impose it as a non-homogeneous Dirichlet boundary condition on step 2 in order to find the pressure difference through a pressure continuity correction finite element approximation. So actually here we treat the pressure difference as by a proper lifting techniques. So we have a here phi, which is a fluctuation around this value, which is phi tilde, which is the lifting given by the non-homogeneous Dirichlet boundary condition applied on gamma n, that we are going to extend to the whole omega by constant values, basically. And finally, on step 3, we are just recovering the right pressure and velocity. So now we have we get the description of the full order model, and as we will see with this treatment of the boundary condition, for instance, when we have, as in the numerical study that we perform, a flow that is going around an obstacle, so we are not obliged to go very far from the obstacle in order to impose the boundary condition, but we we can use this condition for a reduced, let's say, computational domain just around the obstacle, and this will give, of course, a computational gain in CPU time. But this computational gain, of course, can be increased by now considering the reduced order version of this fully discrete time splitting form. So, as I said before, we pass both from an intrusive technique on one side, which consists on a PID Galerkin projection method, and we combine it with the data-driven method, which is based on radial basis interpolation. And on this case, I will going to describe the standard RBF procedure and how to extend it for let's say, longer time interval if we want to do time extrapolation, as in the case that we will consider in the numerical studies. So let's start with the ROM version of the fully discrete time splitting form. So it is based on a POD-ROM methodology. In order to get an efficient ROM, we are completely separating the offline and online decomposition. So we finally ends up with a hybrid POD-ROM, which is projection-based for the computation of prediction velocity and updating the velocity and pressure, which are steps 1 and 3 I described before. And on the other side is data-driven, let's say non-intrusive, for the computation of pressure boundary condition and of consequence for pressure difference by means of RBF, which are steps 1/2 and 2 that I described before. So here, as usual, is to go with the ensemble of known snapshot, and thus with the construction of the POD basis. So here, if in general we go just with velocity and pressure snapshot, for this method we have to go also with other set of snapshot for the prediction velocity and also for the pressure difference. And then we construct the corresponding POD spaces by using the L2 norm in this case for velocity, predicted velocity, pressure, and pressure difference. And so we can see the ROM solution actually as the reduced approximation by considering simply a linear combination of the corresponding POD basis times the time varying coefficient for each field. And thus the proposed POD-ROM, once we have the initialization, let's say by L2 projection, the POD basis of velocity and pressure, then we solve step 1 by POD Galerkin projection. So we consider the same variational form we had on the offline phase, and we project it on the POD-ROM basis for the, in this case, for the predicted velocity, in the case of prediction diffusion reduced order model. And here I pass directly to step 3, which is the updating of pressure and velocity, by supposing that we have already computed the pressure difference given here by phi n+1. And later on, I will describe the radial basis function on intrusive technique that we are going to use in order to compute this phi n+1. So yeah, this is just the matrix form that to which it reduced the system that I described before. So we arrive actually to an autonomous dynamical system for the vector of time coefficient related to the predicted velocity A tilde, in step 1 for prediction diffusion reduce model. And here is the update of the time coefficient related to pressure and finally to the corrected velocity. But as we said, in order to arrive to this computation, we have to consider how we approximate the pressure difference that we are going to use in the time splitting reduced order technique. So as I said, we use an RBF strategy to approximate it. So again, we consider it as a linear combination of the associated POD basis times the time coefficient vector. And now the RBF is used in order to compute this time coefficient vector. In order to do it, let's say the standard technique, which is also included in this paper by Gianluigi Rozza and co-workers, is by using this notation, let's say, adapted to our framework. So what we are going to do is to consider a set of time instances at which pressure difference snapshots were taken, and then T star is just the time instance at which the ROM solution is sought. This is based basically on the fact that the ROM that we are going to consider is as parameter just time. So, but we can actually extend this this kind of discretization also to the multi-parameter framework, in which we consider also some physical parameter and so on, as the Reynolds number and so on. And finally, we get the L2 projection of the matrix of pressure difference snapshots on the corresponding, let's say, POD basis. So we did, we consider this pair of data, and the interpolation using the RBF is based on the following formula, where we have the linear combination of some weights times some radial basis function. Actually, here we are going to use Gaussian function center on this quantity. And the computation of the weights is described here on step 3. So this corresponds basically to a solution of the following linear system, so that at the online stage, once we have computed the weights, we just perform the computation of this formula on the time instance that in which we are interested. Actually, this kind of RBF procedure, which is the standard one adapted here to our framework, doesn't give good results if we are going to perform, let's say, time extrapolation. So imagine that you have a snapshot just computed on a time interval, and what we want to do is to see the behavior, the temporal behavior of the reduced order model in time after this time interval. So for a time window which is larger with respect to the one in which we compute the snapshot. So to adapt this technique to the time extrapolation, let's say, what we are going to do is to replace the independent variable of the RBF procedure, in our case time, which is treated as parameter in this case, by the coefficient of the predicted velocity in our case. And this comes from the idea that in step 2 of the time splitting method, actually the pressure difference is computed through the divergence of the predicted velocity. That's why the time coefficient related to the RBF procedure are approximated directly, not explicitly by time, but by using the vector of time coefficient of the predicted velocity. And so this is an idea that we adapted from this paper of Gianluigi and co-worker to our case. And okay, so we pass now to the final part of the talk, where we actually see the performance, both on accuracy and efficiency of the time splitting algorithm reduced order model that we proposed. So first of all, we have said that we applied it to a 2D flow around cylinders. So here is the numerical setup for the simulation, which is actually the same I already considered in a paper with Julian Ovo published in 2021 on Science Journal of Numerical Analysis. So here is what we call actually here the full spatial domain. That is, this is our reference domain, but then we will see that in order to compute the snapshot for the ROM, we can reduce actually this domain to a domain which is just around the obstacle. So yeah, this is the whole domain for which we impose a nillet boundary condition here, which is a parabolic profile as described here with this with all this value. And then both on cylinder and upper and lower wall, we impose homogeneous Dirichlet boundary condition. And at the end, here is where we have open boundary conditions, which is treated as I have described just before. So as usual, the quantity of interest we are going to control basically are the kinetic energy and the drag and lift coefficient around the obstacle. And to compute these last two quantities, we are going to consider an integral formulation of this coefficient. Basically in order to avoid numerical issues due to the discretization of the obstacle, since we are using relatively coarse grid. And so it is based on these two integral formula, where here the test function are the test function that are described at the end of the slide. So as I said, what we are going to accurately reproduce is the numerical solution of this test, both on the full domain, which is a domain used in standard simulation of this kind of flow, but also if we reduce the computational domain at the alpha and also to this, what we call this minimal domain, we will see how, for instance, quantities such as the drag and lift coefficient are computed almost equally well for this last computational domain, and also the wall fields such as vorticity, pressure, and velocity are not disturbed from the imposition of the boundary condition here, even if we consider this the reduced computational domain. And this, of course, allows us to have a reduced computing time when we compute snapshot. So here is the form setup and implementation. A space discretization for the full order model. We use InfSoup stable finite element pair for velocity and pressure, and on a relatively coarse grid, as I said. The initial condition is flow at rest. Here is the time discretization by considering a semi-implicit BDF1 algorithm with this time step, and implementation finally is performed with free-frame software. So about the form results, you see for the kinetic energy, here is a comparison of what happens if we compute it on the half domain, which is the upper line, and on the minimal domain, and we compare this kinetic energy compared to the one that we compute on the wall boundary, but this on the wall domain, on the full domain, but restricted respectively to the half domain and minimal domain. So you see a good agreement of these results, and also if we compare the temporal evolution from 0 to 7 seconds of the drag coefficient computed on the full, half, and minimal domain, again, we have a good agreement, both in the transition part and then when we arrive to the quasi-periodic states, let's say from 5 to 7 seconds. And also almost the same is for the lift coefficient. So again, we have the computation here of the temporal evolution on the full, half, and minimal domain, and we see that they agree reasonably well. And here is the vorticity, magnitude, and contours of the foam solution computed on the 3 computational domain and at final simulation time. So you see actually that there is no disturb and no distortion practically of the vorticity field here around the obstacle. That means that the same simulation we can perform with the wall domain actually can be performed with this restricted domain. And so here I first give you a consideration on the CPU time, where you see the speed up for the foam solution if we use the full, half, and minimal domain. And of course, so we choose actually to work with the minimal domain in order to compute the snapshot for the reduced order model. And at this point, if we compare the CPU time between the full order model and the reduced order model, just on the time interval where the flow is already developed, and on the minimal domain, we have up to 2 orders of magnitude of decreasing of computational time. So in order to give, let's say, quantitative results on the comparison between ROM and foam, so here is how we compute the snapshot. So we take actually every foam solution just on one period of evolution of the flow, and then we will try to extend the reduced order model for larger time interval up to 7 seconds. So here is the case of the normalized POD eigenvalues for all the unknowns field. And here is how we compare the kinetic energy first. So here is a comparison between foam and POD ROM on the time interval 5 to 7, and the temporal evolution again of the drag coefficient and of the lift coefficient. So we see qualitatively that they agree quite well. And if we compute the error, actually you can see, so here is the L2 discrete in time, L2 in space relative error of ROM with respect to full order model for the quantity of interest we have computed. So for drag, lift, and kinetic energy. And we see that for drag and kinetic energy, especially, we can arrive to relative error up to almost 10 to the power minus 4. And for the lift, we have 10 to the power minus 2. That is a 1% error if we consider a sufficient number of basis function for for the flow fields. And for the velocity and pressure, we can see here the decay again with respect to the number of POD bases of the relative error, both for velocity on the left and pressure on the right. So we have that velocity, we get almost a 10 to the power minus 3 error if we consider a sufficient number of POD modes. And the error for pressure is up to 10 to the power minus 2. So again, we are below 1% error with respect to the full order model. So we consider this result as reasonably accurate, and they give again an efficient computation not only of local quantity of interest, such as drag coefficient and lift coefficient, for instance, but also of the wall flow field, such as velocity, pressure, and vorticity. And we have seen that considering also in the finite element framework, this reduced computational domain, thanks to the application of the particular pressure boundary condition we applied, does not imply distortion of the flow vorticity field around the obstacle, which means that again we have the hope that this is a good strategy, for instance, in order to compute in real application flows such as the wind flow around wind turbines. And we have seen that we didn't need to use supremizer technique at the ROM level. Neither stabilization terms are needed, both on offline and online. And as a work in progress and future research line, as I said, we would like to extend it to 3D flow, also because this kind of time splitting strategy it seems to be really well adapted to a parallelization also of the code. And so we have the hope to get really that we can approach really the computation of 3D flows, and then also the application to multi-parameter settings, in which, for instance, we have physical parameter to the ROM framework, such as the Reynolds number and so on. So here is a list of references related to the code. So we are trying to finish a preprint based on this presentation, and then you have here the other references I already cited inside the paper, and from which we take basically inspiration from both the foam part and ROM part. And also an acknowledgement goes to the project, in which we have created basically this work in collaboration. So starting from the European area project, in which most of us are involved, and then a project of the virtual mechanics enterprise on thermal energy, and finally a project we recently got in our group by the Spanish government on high ROM, let's say, on hybrid reduced order model applied to incompressible flow and neural networks. So that's all from my side. Thank you very much for your attention.
Thank you so much, Samuele, for this really detailed and nice talk. I really enjoyed. And for now, I would like to open the question session from audience. If there's some comment or question, Please unmute yourself or raise the hand. Yeah, first question, I think from Tran.
Okay.
All right. Very nice, Samuel. I agree with you. This was a very nice presentation. So I liked what you said maybe towards the end, like like a couple of slides back, which was so 42 or 43. Yeah, here, right. So I really liked what you said. So if I understand correctly, so it does provide, so time splitting does provide accurate and efficient computation of the, lift and drag coefficients, and you can reduce the computational domain, and then you don't need supramisors and for stabilization, right? So these are the, but I mean, so I understand it, but I have to say, so like, my question is, how about the monolithic ROM? So in the sense that at the farm level, so time splitting is very popular, but I think that the main reason there is that you split the problem into smaller problems, and then it's more efficient. So right, and I'm just wondering. So my I would say that it's important. Maybe if you have a low dimensional ROM, maybe it's not that critical to split the 10-dimensional ROM into 5 + 5. Sure. But I think as we move to higher and higher dimensional problems, like millions and billions of degrees of freedom, I think the reduced order modeling will also have a similar issue. And in that case, it might even be beneficial at the ROM level to take the monolithic ROM and then split it into projection like you did, into projection, so we use time splitting. So it was not a question, it was more of a comment. I think that maybe now is not apparent, right? But
you are right, but what we had in mind at the beginning actually is to attack problem like 3D flows with billions, millions or billions of unknown. And so also at ROM level, maybe you have to pass from 10 degrees of freedom already to 100 or 1000 degrees of freedom. So in that case, maybe you have you can see really the efficiency of the ROM.
I agree.
From monolithic to time splitting ROM.
Right. Okay, thank you. Very nice talk.
Thank
you. Nashdi?
Just a small, hello everybody, just some small comment regard to the question of Traian. I mean, by the way, you need to provide data. So you need to solve the full model, okay? And the idea to make splitting and splittings to be consistent between the initial data that you are solving, okay? Because with million and million, it's complicated to go with the full couplet velocity pressure or to use a saddle point approach, especially in 3D when you have to unsteady. So it means that, by the way, at least with the code we have, we can go with time splitting and we have to implement the outflow boundary conditions. Once we do this, we want to remain consistent. That's why the question to say how we act time splitting versus ROM takes sense. This is the spirit of the work.
Yeah, this is of course Meshti. Thank you for for these details. So I didn't mention, but we wanted to be consistent from the full order model and the ROM in order to not lose precision, basically.
I think there's another question from Ping Song.
Yeah, hello. So I have a question about the RBF. So you were saying with the standard approach, it's not doing well in extrapolation, and you kind of make the coefficient depends on the velocity coefficient. And I'm wondering how far have you considered for extrapolation? Like how far in time? Like when do you see that method does not work?
Okay, so when we started to consider the time evolution of the ROM outside the window, let's say, where we computed the snapshot, so if you remain in the same time interval where you compute snapshot, it's all okay. But then if we go very far from, let's say very far, if we go far from this time interval, then is when you start to see that the standard RBF approach start to give some numerical issues. For instance, the increase of the kinetic energy in the in the POD solution and so on.
And with the modification,
you are able to maintain, let's say, stable in time the solution. So you do not know any increase of the kinetic energy. So you see here. So if the first period ends here before 525, let's say with the standard approach, we started to see, let's say, at 6 this kind of behavior. While here you cannot see, of course, more longer you go on time and you start to see some differences but it seems to remain stable, let's say, around this value, the POD ROM, with this technique.
I see. So there's some discrepancy, but it will remain stable further in time.
Yeah.
Okay.
Yeah.
Thank you.
Thank you.
And any other further comments or questions?
Yeah, maybe I can ask a question. I think it was on slide number 10 or 11 where you introduced the, say, modified boundary conditions.
Yeah.
For the pressure.
Yeah. So here is where we start to.
So what I didn't get is so the other one that you were showing. What I didn't fully get is that this derivation on x1. So you choose x1 rather than x2 or whatever else because you knew a priori that the outflow boundary was vertical.
Yeah. Okay.
So, like my question would be, would there be a way to generalize this to an outflow boundary which has another shape? It's not like a vertical line or an horizontal line.
Yeah. Okay. So I think it can be done maybe by splitting let's say the derivation on the basis you have on this shape. So maybe you have to work or to combine, let's say, the different direction of the basis. But I think we didn't try it. I don't know if if it can be possible, but I think this could be the let's say the
way to go. Yeah.
The way to go.
Okay.
If you can, if I can give a comment, not for the reduced model, but for the full model, in the paper cited by Samuele, we provided generalization to general coordinate.
Okay.
And I went to the local basis, which is made by tangential and normal, and we write the same technique. I mean, we can extend it to any curved outflow boundary condition. But I have no idea about how it will work with respect to reduced model. Okay. But it was only formally done. We didn't apply it really with a numerical example. It was just because the reviewer asked the same question than you. So it's okay, let's make local, and we did it. But we never applied to concrete problem.
2011 was before my time, so I definitely wasn't a reviewer. Okay, thanks.
Okay.
Okay, I think we have all comments and questions, and I would like to thank our speaker again. Thank you so much, Samuele, for this nice talk again, and see you next week. Bye-bye.
Bye. Bye. Ciao.